Welcome everyone again. Now we continue with the set of lectures from Arkaitz in the quest for Exotica. Welcome everyone again.
Sorry.
Oops.
It works. Okay. Yes. So we finished by taking a look at this test here. This moment. These are what I call the vector measures. So they have unique angular momentum. You can also call it the same if you want. The idea is, in this lecture, we are going to take a bit, just a look at the quark model construction of these guys. I don't want to get into the details because we are not going to do exercises predicting anything with the quark models, but the quantum numbers. So all I care about now is going to be defining quantum numbers that are going to give us possible strong decays, and then we will go into decays. So we saw the pseudoscalar measure effect. We saw where they are so light, and then I introduce you to the vector measures. For example, this is how I would describe the quark construction of the piles. Remember that I am just for convenience, for simplicity, not doing the second section of these guys. But you will always see this, that you always have to symmetrize. For simplicity, they most of the times never give you the full thing. And we're going to take a look at this and the way they are built on the quark model. Remember, I don't care much about the details, and so I will just pass right through it. So let's start with a single quark. We have a lonely quark that has spin components, then some spatial wave function, then the quark part and the color. And we're going to build, remember that our hadrons are color singlets, so that our part is going to go. We're not going to look at the color part of a quark anti-quark construction, but then it's going to have some basic quantum numbers. Again, this symmetrization or the symmetrization. The idea is that these basic quantum numbers, if I was to write in this horrible formula, I only care with you realizing that it's going to have some Klebskor times, we saw the tables before, that are going to tell us how we build the total spin and angular momentum of the hadron by using the quarks. So the ones that we got from the table before, and then some wave function for the spatial component. Now we are going to write it in the spectroscopic notation. And the idea at the end of the day is that we can recover a formula like this, where we have some quark structure here with some symmetrization. This means, if you remember, if you don't, I have the formula here, that when we apply parity transformation here, and we are going to flip the wave functions now, we are going to recover a -1 to the L, depending on the angular momentum of the object. So whenever we have a hadron built by quarks, we will have the -1 to the L, depending on the angular momentum of this hadron. And then a +1, because parties of quarks and the quarks are opposite, right? So plus and minus is minus. So this +1 because we have quarks and quarks. If we do that for charge conjugation flips the particle to its antiparticle, right? And so we're going to recover a -1 to the L for the angular momentum and another -1 to the L for the total spin. So the message to take home is, if we build measures using a quark model, not all quantum numbers are allowed. If I am going to use JPC, so angular momentum, which we said is a fantastic quantum number, and then parity and charge conjugation to define our states, only some of them will exist in terms of the quark model. For example, for total spins, singlet means spin 0, triplet means spin 1. These are the quantum numbers that are allowed for JPC. So what would happen, can somebody tell me, and this is very important for us. So what could happen if on a triplet system, we determine in an experiment a particle that exists in 1 minus plus quantum numbers? Parity negative, charge conjugation positive, and then the total angular momentum is 1. Is it in this table? It's not in this table. So what is it? What is it made of? Well, certainly not quark anti-quark. Can somebody tell me, that's what people I get together first time in, can somebody tell me what is a 1 minus plus object? How do we call them? Yeah. A hybrid meson. We will see what a hybrid meson is. Hybrid meson is a strong word here because a big chunk of the experimental program in this building is devoted to hybrid mesons. The detector upgrade Gluex is devoted to hybrid mesons, so we'll play with that. So now let's go back to something simple, the vector mesons. We had 9 here, and I just put it to this side, 3 of them. So let's say that JPC was everything there was, and these are all the quantum numbers we care about. Well, J and P for these 3 mesons are basically the same. This one doesn't have like a properly defined charge distribution, but the other 2 have. So they are more or less the same in terms of this quantum number. But the quark and the quark construction is not the same. So wait, we are going to classify things from quantum numbers, and then we got the same quantum numbers, and then these 3 objects look massively different. This doesn't seem to be all there is to the, these particles, right? We are going to need something else. Well, first things first, let's check that everything works. So maybe the quark model doesn't. If we were to calculate the transition from an E plus E minus related through a photon to 2 quarks, and we do this for the rho 0, okay? Why the rho 0? Why not the rho plus? Because photons have no charge, so it must be rho 0. So if we do this for rho 0, then we get something that is proportional to this term, depending on the charges of the quarks. If we do it for a phi, for example, we will get a term like this. And if we do it for an omega 0, then we will get a term like this. So they should appear, or basically the decay should go in the ratio 9 to 1 to 2 when we do rho to omega to phi. What is the experimental data? Well, it's fantastic, right? Perfect within uncertainties. So yes, our model works. So we are missing something else. We need some more quantum numbers. If we, for example, determine the decay of the rho 0, it goes, and I'm telling you, to pi plus pi minus. This leg here is connected now through a gluon. So these are connected quark lines. This is its main decay mode. Will this decay into pi plus pi minus because it has the same JP? It cannot because that's a strangeness. Will this decay into pi plus pi minus if it's neutral? Well, it will not because there is something else, some other symmetry preventing it from decaying to 2 pi's. I mean, I never included the isospin in this list, but I was telling you that it was very relevant, and it's even in the title, right? So we better include it as a quantum number to describe our states. But what is this G? Can somebody tell me what is this G? So this is what we call G parity, and it will be very useful for some of these decays. You'll see, in particular, for things decaying to pions is, frankly speaking, trivial to realize, or very easy to realize to how many pions something can decay reducing G parity. So in order to define it, we're going to do some hand-wavy group theory because I'm not going to describe everything in detail, but I can give you quick books about that. So first things first, out of the 3 components of the isospin, the second one, y-axis, x, y, and z, the y-axis commutes with the charge conjugation rate. And we're going to use this. Now, the second thing that we're going to do is we're going to define a rotation of 180 degrees over the y-axis of isospin. So if we had this, our axis, this would be a 90 degrees rotation, right? We want 180 degrees. So basically, we are going to get the isospin sub x, and we're going to flip it to minus I sub x. We're going to get I sub c, and flip the sign. And this is what we get at the end of the day. Of course, the isospin in the y-axis remains invariant because we are rotating everything around the y-axis. So that is the remains invariant. So we are going to build this operator, which is the charge conjugation times this rotation that we just did. And because charge conjugation and I sub y commute, and the rotation is just the exponential d, at the end of the day, these things commute. Okay? So this is the G parity operator definition. And let's do an explicit example with pions. If you go to the PDE, to the book, and then you look at the state, it's defined by isospin, G parity, and then J3C. And so it's minus. Let's calculate it. The rotation in terms of pions, looks as matrix like this. So now we have a triplet, 3 pions. This rotation operator is a 3 times 3 matrix, right? And what does it do? What does it do? Okay. If we have a pi plus and we rotate the isospins of a pi plus, let's say that in this rotation we're flipping the third component of the isospin of a pi plus. Where does the pi plus go? It goes from pi minus, right? We flip the sign of the third component of isospin. So we went from +1 to -1. This is the pi minus. And then if we act with the charge conjugation operator on the pi minus, is minus the pi plus, with the usual definition of the convention of the charge operator. So we got a -1 sign, which is the one here. Also, for the pi 0, which is in the middle, right? The rotation in this definition is going to change the sign. So the rotation acting on pi 0 is going to give me minus pi 0. And now the charge conjugation over minus pi 0, well, it's going to give me minus pi 0 because the charge conjugation of a pi 0 is plus. So again, it gives me a -1 sign. So in summary, finding this operator this way, finding G parity this way, all the signs of this operator acting on a system that has well-defined parity, G parity, are the same. Or basically, if you have a multiplet with well-defined G parity, then the sign is the same on every element of the multiplet. This is why we define it this way. If you have like a well-defined isospin, like for example, an integer isospin, then you can prove that this is the following. And I won't do that. But I can lead you to the books that do it. So any question about this G parity operator? Or these quantum numbers that we're going to look at?
So you say you need 5 total to describe the pi knot perfectly. But if you go to like the previous slide, G is written already in terms of C and I. So would that mean that you only need 4 of these quantum numbers?
Oh, you mean this? Well, the thing is, as I said before, this always happens when you have a well-defined isospin that is an integer. There are objects that don't have well-defined G parity. So there are objects that won't have this number.
Okay.
So in principle, you put all the numbers that can classify all of them. And then some of them won't have G parity, for example, so it won't be a good number. But yeah, if you knew C and if you knew the isospin, then of course G parity is trivial. So the idea is that for some states it's very easy to see where they're decaying to with an isospin and G parity combination. And also because this is only flip sign, I'm pretty sure that you could have systems, complicated systems, where different isospins give you the same sign for G parity, right? So it'll be kind of not redundant unless you have it right. Any other question?
Maybe a big picture question. How should we understand the success of the quark model in describing the spectra, given that it also describes the proton, the total quantum numbers, but we know microscopically that the spin orbital angular momentum of the proton looks nothing like the quark model. So is it getting the right answer for the wrong reasons? Is it expressing the right answer in a different way? How do you think about that?
Always. So first things first. Well, I don't really work on formal descriptions because I'm not a heavy supporter of using it always in a spectroscopy of what we do. But it is true that, well, the idea is, if it was completely incorrect, then we couldn't be getting balanced pictures out of some hadrons. And so there will be this interrelation between being able to define a proton as 3 balanced quarks and having a quark model that gives us something like a proton. I found always very interesting that it calculates some things like the masses of some hadrons right, but then some other things like decay rates or some of the properties are completely out of question by orders of magnitude. So it's not only for protons, it's also for mesons that something is well predicted by the quark model, the balance picture usually, but then everything that looks beyond that is horribly wrong. In this case, we are going to use it only to motivate the states that do not have quark model, the quantum numbers, and also to motivate interaction of these quantum numbers. Yeah. Any other question? Any question online? So let's go into the case. So I introduce you to the rho 0 decay to pi plus pi minus. Fine. Now, as I said, this guy has different, well, this guy has an isospin 1/2, so it doesn't have well-defined G part in this case. But because it has isospin 1/2, we can see what is decay, right? It couldn't decay to a certain number of pions because it has like an integer number. So this would be 0, 1, 2. It has to have something with isospin 1/2 because it has a strangeness. It's going to decay mostly to pi, right? Makes sense. But now about the omega. The omega is pure light. And in principle, you could think that it also decays to pions, right? But the G parity of the omega is not plus like rho, it's minus. So what does it mean? G parity is a multiplicative operator. So if you have 2 pions with G parity minus, then the total G parity of the system is plus. If you have 3 pions, then it's minus. So you see now it's so simple to see these kind of decay channels from particles that have well-defined G parity. Because if it's a negative number, then it will be an odd number of pions in the final state. If it's positive G parity, there will be an even number of pions in the final state. So it's telling you where to look for. And these guys are very interesting. So, for example, I introduced before the fact that if you want to look beyond the standard model, and you want to, for example, describe the Hadron vacuum polarization to the anomalous magnetic moment of the muon, or the super long sentence, if you want to predict these red values that are very precise, you have to describe with utmost precision the rho and the omega line shapes. No way around that. It's the main contribution to this number here. So if you were at the end of the day to claim that exists beyond standard model physics, you better do a good job tackling this down. And the K star somehow enters the calculation of the decays in the fact that these are dimensional decays to our processes. And in the middle, you have a final state of IK dominated by the K star. So you better get this one right. Now, problem is, we were talking before in the previous lecture about the distances that some objects travel, right? Well, these are the distances that these objects travel in the restaurant. So, if you are able to build a detector of the size of the travel distance of these guys, give us a call. Okay. The problem here is there is no way we can see these ones. They are not particles that live or they are stable through QCD. They decay through external interactions. And so they are called resonances because they are not stable. Now, how do we measure these guys? How do we determine them with precision? And so this is what we do here. These guys are going to decay to other particles. And so they leave tracks. So let's say that we are, I think this is, this might be CLS or Atlas. So if we had 2 beams of particles colliding with each other, and then it was to produce a rho resonance at some point inside chamber, inside the calorimeter here, this will decay a very short distance. And then it will decay to 2 pions that go in opposite directions. Now, I detect those 2 pions, and a supercomputer counts all these hits. At the end of the day, can reconstruct the decay of this rho. And by studying the properties and the way these 2 pions were created, infer properties about this rho resonance. This is what we do in accelerators. Some particles are easy to detect than others. This depends on the design of the calorimeters, and we have experts working on that. And of course, as I said before, you have to have a right idea when building an experiment of which particles you want in the initial and which particles you want in the final states in order for all these to work. So as a summary, in accelerators, we get our particles, long-lived particles, we accelerate them to high energies, we smash them against a target or against each other, and then we produce lots of products that we are going to collect. So now, how is this related to QCD? How is this related to amplitude analysis? The idea is the number of hits that we count are related to the probability of a given decay to be produced. This is quantum mechanics, quantum field theory, nothing new. So whatever we do here accelerated, at the end of the day, it looks like this in the data. And this is going to be related to our amplitudes, to these transition amplitudes, decay, processes, scattering, etc. So let's start by defining, again, my favorite variables, the Mandel subvariables. So if we have a process of 2 to 2, we can define these 3 variants. let's say that particles have no spin. They are, let's say, 2 pions going to 2 pions. In that case, we can define there's just 3 particles and express or formulate everything in terms of just these simple invariants. So this is going to be the S variable, which runs in this direction, is the invariant mass of the system. This basically is measuring the angle between P1 and P3, and this will be measuring the one between P1 and P4. Okay. Did somebody finish the exercise that I asked before? Okay. So we're going to define a transition amplitude. So this is going to be the S matrix. This is what I care about the most. Let's say that I have a system alpha in the initial state. I don't know what alpha is, but I know it's in the initial state. And then I have some collection of particles in the final state called beta. In the asymptotic time where they no longer interact, I collected some beta particles in my perimeter. So the transition from alpha initial state to beta, sandwiches between this S function, is called the S matrix, which is gonna encode everything that is happening for alpha to become beta. Okay? Now I don't have an algebraic expression for this in general, but I'm gonna describe this in terms of very basic first principles that the theory has preserved. The first one, so once a wise man said, 100% of the times quantum mechanics, something will happen. So you don't know this guy, but we do. And this translates into the unitarity equation, which means if you start with a system of particles, and then you collect the probability for this system of particles to decay to everything, and you collected all of them, theoretically you can do that, experimentally that's another question, then the probability must be 1, which means that this operator must be unitary. When you are calculating, for example, let's think about one single channel. This is a matrix, but let's think about one channel, pi to pi, and only that can happen. Then this is a function, right? And a function times its complex conjugate is the modulus of a function. This is the total probability, which must be equal 1. So yes, unitarity is a basic principle. So we are going to adopt this. Now it's ours. Now we're going to define this S matrix as the identity plus something. Why? Because inside this S matrix there are many processes that can be encoded. One is the trivial non-interactive process. Let's say that I have 2 pions in the initial state, and they are too far apart. They don't see each other. And then I end up with 2 pions in the final state. Well, I don't really care about this reaction because nothing happened in the middle, and I want to study QCD interactions. So this identity, which is the trivial reaction, is going to be subtracted from S. So S minus 1 is what we want, the T matrix, the amplitude. Now, because this is unitary, you can do this as exercise. This is a unitary equation for T. And what we are going to prove in the next lectures, Friday, is the optical theorem. The dx, as I promised before, we count the number of hits on the detector. And this is basically the total cross-section of a process. This is the total number of hits. And this, the optical theorem, can be related to the amplitude for a given set of one-dimensional variables. So yes, if we get this on an experiment, then we got this. And this is what we are hoping for. So let's start motivating the idea of resonances. First things first, once again, remember, angular momentum is conserved. It's a fantastic quantum number. So we can get the amplitude T, capital T, and then we can split it in different angular momentums. It's what we call the partial wave expansion. So what we are doing, all we are doing is basically extracting the orbital angular momentum part, and then we will have partial waves inside that have some different values, of course, depending on the energies. And these guys have well-defined angular momentum. Okay, so let's take a look at quantum mechanics. If we have a system that is an eigenstate of a Hamiltonian, we have a system that lives forever, right? Because if we solve the Schrodinger equation, then we know that the evolution is e to the minus I times ht. It's an eigenstate now. So this h is just going to be the mass of the state. So this thing is oscillating over time, which means that the probability of finding it never decreases. It lives forever. And this is what we call a bound state. Do you know examples of bound states in strong interactions? Protons? there is one very interesting. The deuteron. You guys know the deuteron? The deuteron is a bound state. It lives forever. There are strong interactions. It needs to be created by two nucleons interacting with each other. So this is kind of the wave function for this kind of objects. But what happens with a quasi-agent state? Let's wave a bit. So now this energy is no longer real. It has some imaginary part because it's not fully an agent state. As we multiply with I, you get a term that is real. I am writing it this way, so we see what happens. If I get the probability for this state to live at a given time t, then we see that this thing is fading away. So the probability of finding that state at a time t is decaying with an exponential. What's happening? I mean, the state is disappearing, is decaying, right? If you go to times t infinite, then there is no probability to find it. We say that usually it lives for 1 over gamma, is the suppression 1 over E, right? Which is a kind of a standard definition of the lifetime of something. So if you go get this amplitude, remember, this was quantum mechanics. We are in relativistic description, but if you go onto a Fourier transform of this to change from the t variable to the energy, okay, that is going to be our x-axis, then this kind of exponentials end up being what? They always end up being, the exponents end up being part of our denominators. Okay? So this is almost a pole. If it didn't have this gamma, it would be a pole on the real axis. Because it has a gamma, it's now a pole where? On the complex plane, right? If E is m minus this part, then it's a pole. So experiments are run in the real axis. If not, start. But the idea is very close by to this real axis where we measure things, we can have poles. And these are going to create peaks in our amplitudes. Because very close to where we are measuring in front of it, we have a huge pole. So we are cutting part of a mountain, right? And this is what we see in the amplitude. Okay, so what is this? This was the interaction to the light spectrum. So these are different colors, bunch of peaks, green, red, whatever it is. What is this? That is the Higgs boson. I mean, it was an incredibly challenging definition, but basically determination and construction of the accelerator and everything that gave birth to the measurement. But from the amplitude analysis point of view, this is as trivial as it gets. It cannot get any simpler than a bright linear formula, which is what we are giving you now. It means it's isolated, it has a very nice peak, and it's a simple resonance. So it's a pole in the complex plane, very close to the real axis where it's measured. Okay? And with that, by fitting this data, we can determine its mass and its decay width, or basically the inverse of its lifetime, right? Now, how does it look for us in hadron physics? Let's say that we have, as I said before, pi to pi, so it's elastic. In the elastic region, the amplitude will be described with a modulus and a phase. That's all there is to a complex function. So the modulus will look like this, with this formula, with the Higgs. And the phase will look like this rapid phase motion that we have in the plot to the right. This is the relativistic gradient formula. Okay, so we have a toolkit to fit things and to describe it, right? And for many, many years, this was a very successful tool to hadron spectroscopy. You have lots of different peaks and can be well described by this formula. And so you can extract all these levels in the spectrum, its masses and its widths. However, light is not so simple. And many other reactions, particularly the ones that we are looking at nowadays, are much more challenging. So whereas you can look at peaks like this and describe them with brightness for the rho that we've been talking about, getting its excitations, like the rho prime, is not so simple. And these formulas break. What happens if we do, for example, 3-particle decays? Everything I did was 2 particles to 2 particles, but QCD doesn't prevent us from having 1,000 particles in the phase. So what happens if I go and look at 3 panels in the phase? Well, we don't really have the formals, we're just started to apply. Or what happens if we look at non-trivial structures, like the lambda 1405, a resonance that is apparently two poles almost together. This is definitely not driving a resonance, right? What happens with the simplest, lightest scalar meson nonnet? So I introduce you the pions, kaons, etc., and vector mesons. What happens? These guys are very closely related to the vector mesons. They are produced in pike interactions, and they are like the vector mesons, like the rho and omega that I introduced before, only they don't have angular momentum. The angular momentum is 0. Well, does this guy look like the peaks that I was describing before? Does this one look like that? Is this peak a broadly straight and smooth, like the one I showed you before? No. None of these can be described by this formula. So, do you have any questions about how to do this? Basically, we got to a bypass where our formula broke. Do you know how to solve everything? Yeah.
Oh, I have a question. I don't know how to solve it. Maybe this is kind of what you were getting at, but is there a technical difference between a particle and a resonance?
Well, so a particle, for example, particle like a kaon, that's in the kaon electron interaction, right? It's a stable particle under QCD. But it decays under the electroweak reaction, right? So it has some lifetime. So in that sense, kaon is a stable particle in QCD, but it's a resonance in electroweak reactions. It's just here we are forgetting, because strong interactions dominate everything, we are forgetting about electroweak and electromagnetic decays. We are only caring about what happens in QCD, because we are studying QCD. But for example, well, I'm not going to go back to the previous PDF that I had for the first lecture, but if you remember KS and KL, K long and K short, are eigenstates of the Hamiltonian, right? And they have well-defined CP numbers and everything, and we looked at the mixing and evolution of a K zero. You remember that there were some parameters on the probability equation that are the gamma S and gamma L, because they decay according to wave processes.
Particle decays under a given interaction. It's a resonance.
It's no longer stable.
It's a resonance in that interaction. If not, it's a.
Indeed, well, it's a particle. All of them are particles, but it's a stable or not stable. So under QCD, these guys we're talking about the pions and the kaons are stable, but they are not stable. For example, I is not stable under the electromagnetic force, right?
So like a neutron is a resonance for the weak interaction.
Well, yes, if it decays, yes, then it has some lifetime, and then you can call it a resonance because you can associate it with a mass and then a lifetime. So at some point, the propagator of that particle, provided that in the denominator part, is not on the real axis. It must be a bit deeper into the context.
So you talked about detector and how we measure the decay products and not the resonances, right? Because they're short-lived.
Yes.
Now, if let's say there are two resonances who have the same decay products, how do you differentiate between one being?
Oh, that's a very interesting question. So unfortunately, that's a very complicated one to answer. But usually, what happens when two resonances decay to the same products, right, is let's take a look. This is gonna make it simple. So can I see, like for example here. So here you have two resonances, upsilon resonances that decay to the same products. This is the same in biomass. I don't think you see much because it's a horrible low resolution plot, sorry about that, but you see this big, right? And then you see the second one, which is an excitation. And you can tackle them down because it's narrow enough. So in the biomass, you show first one, then some space, and then the second one. Also in the energy, the variables that you can determine in your experiment, they didn't show up on top of each other. The resolution in the energy, because they have different parameters, make them split apart, right? Yeah, indeed, I mean, the momentum is different. They show up at different energies. So they show up at different momentums. So if you are doing everything in terms of the phase space of momentum, then they show up at different points in the energy. And so you can tell me, you know, this is the ground state of this family, this is the excitation of this one. But it can happen, and we will explore it in the next lectures on Friday, that some of these overlap. like a big overlap, and then things get much more challenging. But this is what we are, well, where we are heading to partially. Okay, so let me continue because I still have to finish this part. So let's say that this was all too complicated. We don't like it, and we are tired because it's the afternoon. So we're just going to move on. We are no longer going to look at experiments, and we're going to go into the Lattice QCD mode. Lattice QCD is a numerical approach to solving QCD. So instead of measuring a detector and everything, we're going to use a supercomputer. And what we are going to do is our space-time is not going to be a box. Okay? A discretized box. So you're going to have some points, some space-time points. So the good thing about this is that it's non-perturbative, so we don't have to fight against things that don't want to converge because they are not friendly to us. And it's systematically improved. So we can make our boxes bigger and our spaces, basically our grids, finer. So less coarse. Now we have to do a collection of steps. And I am not going to look into, well, basically, we're not going to go into detail because all I'm trying to use Lattice QCD for is a motivation to amplitude analysis. But let's take a look at this. So in Lattice QCD, what we want to calculate is called correlation function, like this. This is the birth textbook definition. So if you open a book on QFT and you look for a correlation function, this is how it looks like. There's nothing new here for Lattice QCD. Now the thing is, in the Feynman formulation, that you will have to sum over all possible paths in the continuum, right? But in Lattice QCD, all these integrals become multidimensional integrals on each one of these possible points in the lattice. Here you have 4. It will be a 4-dimensional integral. For this variable must be integrated over all possible values the field can get at this point. Okay? So we're going to have multidimensional integrals, huge multidimensional integrals, and we are hoping to solve the numerical. Well, what is the path of Lattice QCD? Well, the path is that if you were looking at these correlation functions, then this is a highly oscillatory, like terribly highly oscillatory. So have you ever tried to integrate something that oscillates super fast? And you know how much precision do you need for this? Yeah, you can always answer the keyboard and try to do it, but it doesn't really work, right? The second one is that you need to do, how high of a high-dimensional integral have you performed by hand? Like a 3-dimensional integral? Well, for an ordinary lattice size nowadays, you will need, roughly speaking, a 20 million dimensional integral, something like that. Yeah, I've never solved one of those. So we are going to go in kind of like different way, like perpendicular to this. And we're going to define imaginary time because we can. So I times S, so I times the action, is going to become just minus the Euclidean action. Okay? And now, if we do that, well, of course, the temporal variable is kind of a space-like now. So we went from Minkowski spacetime to Euclidean spacetime. Fine. The second thing is, for the partition function, which is, again, textbook definition, looks like this. We can, first things first, if you don't remember, I tell you, we can perform algebraically the fermion integral. So there are some variables, then we get this action, and we split the fermion part plus the gluon part. And then there are some variables integral over there with the fermion action. This is the determinant of what we call the direct functions. Okay? And you can perform algebraically because they are Grassmann variables. And now the second part is the gluon, basically the gluon action that has a minus sign with the exponential. So this is bound. It's like probability line, right? It's between 0 and 1 because that is a real number. Okay, let's keep going with this probability thing. Let's see what we can make. So how do you perform integrals? You usually solve them algebraically, right? How do you perform the integral of 1 between A and B? Well, that is B minus A. If you normalize it, then it's 1. But what if I want to perform integrals by averaging values? Because I don't know how to perform integrals. So what is the average of 1 if I sample many times? What is the average of 1 if I sample 100 times? It's 1. If I sample 1,000 times, it's 1. So the integral of 1 and the sample and average over 1 is the same. What happens if I sample x here? Let's say that I integrate x between 0 and 1. What is the integral of x between 0 and 1? is x squared divided by 2. In 0 and 1, it means 1/2, right? If I sample uniformly, this is important, between 0 and 1, and I have one average, what is the average? So let's say I have 2 points. One is at 0, the other one is at 1, and I have the average. It's 1/2. Let's say I sample 1,000,000 times, and so I have a continuous uniform distribution of points between 0 and 1, and I average that. What's the value of that? It's 1/2, right? So again, integrals can be calculated as the limit of an average sampling. If you know the probability distribution, you should be sampling accordingly. So this multi-million integral, actually this part, these U are the gluons, part of the fermions, we did algebraic. So we are not going to calculate this millionth dimensional integral. What we're going to do is sample our observables and do averages. So we no longer have to do a million dimensional integral. Yes?
So you have to be concerned about the loss of information due to the fact that you cannot completely define an arbitrary distribution by its elements.
So the idea is that the probability distribution, you can calculate, you know the explicit formula for the probability distribution. So it's about getting it right. It's not that you have to infer it or build something generic. You know the probability distribution. It's this one. I'm giving it to you. It's this one. So you know it algebraically. Now the problem is on you to produce an algorithm that calculates on every gluon link. So on every one of these values for the links that are distributed according to this distribution. So that is on you to do, and we are not going to go that way. There are tons of algorithms. Some better than others. They usually take you lots of time, but at the end of the day, you can get something. And indeed, you have some uncertainty associated to that. So Lattice QCD doesn't give you a value. It gives you a value with a measured error, hoping to estimate all these errors properly. So now our observables are samples according to, some probability distribution of these links, and then we are just going to do an average. Usually, probably, if we want something good, thousands of average, right? So we have to sample thousands of times the gluon picture. So the idea is we care about mesons, so we better calculate on our observables a quark anti-quark system, because mesons are built of quark anti-quarks, right? So unless we calculate them on the lattice, then we are not going to be able to calculate mesons. So this horrible integral, again, you can split the fermion and the gluon parts of the integral. This is the gluon part of the integral, and this is how the fermion part looks like. If I didn't have this quark anti-quark part, this would be again just like the determinant that we did before. But now we have this quark anti-quark. So this ends up being this d minus 1, which is the inverse of what they call the Dirac matrix. Now, the last step, this integral, once again, is just now sampling over pictures of you with a given probability distribution that is complicated to get and very expensive, but we can do it. So we got our basic building block. It's a huge basic building block, because remember, it's connecting points in the lattice, every point in the lattice. This can be millions, and this can be millions. Okay? So it's a huge matrix. Oh, sorry. This is usually around 100,000. So it's a huge matrix. So now the idea is that when doing these propagators, we can build patterns. What is the definition of pattern? As I said before, is UD bar. Okay, the explicit one includes a gamma 5 inside, because can somebody tell me why is a gamma 5 in my pattern and not a gamma 4? Indeed, because the parity is negative, so it must have a gamma 5. So this is my pattern, and this is my pattern. And the contraction at the end of the day, basically we get the D bar with the D bar, and then we get the U with the U bar. And this is how we pictorially, well, this is a very ugly plot, but this is how we pictorially describe contracting a pattern in the lattice. Okay, so we did all this, we got our clever algorithms, and then at the end of the day, we got the evolution of these operators on the lattice for a pattern. Why do we care about that? The thing is, we no longer have Hamiltonian evolution, right? We went to imaginary time. So this exponent is now a decaying exponential. And those energies, because they are again exponential, we can fit very well. So when I put a system of particles here, let's say pions and excitations of pions, I end up recovering lots of these. As many as systems I put here for the basis, okay? So I can get this from lattice, and this is actually a result with the error bars. So you see the energy is a value, central value, and it has some error bar that probably the people in the back don't see it, but I promise you there is some error bar over there. So now why are these energies relevant for us? I mean, okay, fine. You want these energies, what are they? Good thing is we can relate them to the continuous Minkowski space-time world by just realizing that this box has some periodic boundary conditions, right? It wasn't an infinite box. So in order for everything to work, I had to define some periodic boundary conditions. And let's start with a one-dimensional example. I get two pions, and I put them on a plane wave, and I throw them into the box, like one-dimensional box at 0. So it looks like this, into the I get 0. And then at some point they interact inside the box, and they go all the way to the end. So at the end of the box, what we get is L, right, the size of the box, plus something. This something measures the interaction between these two pions. This is called the phase, right? Now, because I have boundary conditions, and I define this ordinary ones, the simplest case, we recover a quantization condition. You probably have done in quantum mechanics exercises like this with explicit bases or without interaction, so you get the quantized levels. These Kn are the quantized levels in the box. These Kn are the energies we are determining in the box. These are the quantized levels in the box. So what is this equation at the end of the day? This is an equation that tells me what the phase looks like if I give you the quantized levels in the box, which I just calculated. So what this equation, and now it's cut by Zoom, what this is telling me? It's telling me that if I calculate the energies, they become, it's okay, so if I calculate the energies, they become the x-axis on my equation, right? This delta is defined with Kn in mind. So Kn is the x-axis. So I calculated this myself from the computer, the supercomputer, and then I'm going to just flip it over. It becomes my x-axis now. And wherever I have one of these, by this equation, we will have a value for delta. Using this point and that. So why did we just do? We went full circle. So we didn't want to do the experiment because it was very complicated. We went the Lattice QCD route, and then we write it very simply. For a summary, regardless of if you work with a super accelerator or a supercomputer, you have common grounds. You must do what we call amplitude analysis. And here, we are going to impose very basic principles to extract the observables that we want to get into QCD or other possible processes. So I had a few slides to motivate the next set of lectures, but I'll stop here. So any questions?
Yeah, let me remind our remote audience that you can also make questions. You can raise your hand in Zoom or type it in the chat. So after a reminder, please go ahead if there are any questions in the room.
Yes, please.
Can you guarantee that you can always wick rotate?
No, not myself. But in principle, it's something that doesn't seem to be terribly problematic. But as I said, I mean, I don't know of like full proof of that.
More questions? Yeah,
Yes, please.
So was the purpose of using imaginary time in Lattice QCD to turn the oscillations into exponential growth or decay?
Indeed. It's just to turn highly oscillatory integrals into something bound by probability, so we can sample with averages over probability distributions.
Going back to resonance weights.
Yep.
When I look through the PDG, for example, the
Yep.
branching ratios for decaying mesons are quoted in terms of the right Wigner widths. But I also have been told to understand those bracing ratios as a relative probability of those decays occurring. And so does that mean it's guaranteed that the sum of the branching ratio, the sum of the widths is equal to the width of the original particle to give you a unity probability?
Yes, indeed, it should be. I mean, you are going to have some missing for other possible reactions, electromagnetic and electroweak, but that is always going to be totally negligible. So the sum of all the branching fractions for different channels will always amount to the total branching fractions, to the total width of a meson. Otherwise, then you are violating unitarity. If you think in terms, probably just of what you asked, you know the K-matrix approach, we will introduce on Friday. But if you think in terms of the K-matrix, and then all these branching fractions don't amount to total width, then you would easily see that you are just violating this unitarity principle.
You are next, I think.
I haven't really thought about this much, but how, when you Wick rotate and you relate the generating function to the partition function, how are the thermodynamic quantities that you can extract from that related to analogous form factors that describe similar quantities? Like,
So when you Wick rotate, naively speaking, not all quantities that you calculate on your Euclidean action now are trivially related to Minkowski spacetime. Well, there's actually there are a few papers proving that. So not everything you calculate on the Euclidean wall now on the lattice can be one-to-one related to the infinite Minkowski spacetime. So there are many things that you have to be careful of. For example, these amplitudes, these correlation functions are not trivially related, these energies are not trivially related to our amplitudes. We did this quantization condition, which is a simplified version of the actual Loser method, which is much more complicated. So there's no trivial relation in general. There are some other quantities that can be related trivially. And also, as a kind of summary, when you Wick rotate, you are changing from your QFT to a statistical theory. And you have a partition function, and then you have these lattices usually have a defined temperature because of the finite total time extension. And there are some things that you can calculate that are related to statistics on these lattices. There are some others, like for example, introducing some chemical potentials that are very challenging because they induce some other problems. But yeah, you are related QFT and statistical theory will be that.
More questions?
Any more questions? If not, I'm going to go into my 3 slides. No equations.
Okay,
If you
sure.
guys want. Fine. So, yes, to introduce you things that we've been talking about. So these are some examples. We have again the full list of mesons. This is QCD, even that's all of this. And this is what we've been talking about today. But there are many more that can happen, right? We could have tetraquarks. We have a pair of quarks with a pair of antiquarks. We could have what we call molecule-like components. So for example, 2 pions bound together, mediated by remanence of a force, right? Principle that also happens in nuclei. We can have hybrids, and this is what a hybrid looks like in the valence picture. So quark, antiquark, and a gluon in the middle. And then we can also have the beautiful Bataglia plot gluon, which is an object just made of glue, right? Gluons can interact with themselves. So in the vacuum quantum numbers, we can have these kind of objects. And we do see states that resemble them experimentally. It's not that they are hidden. You don't see anything there, but I promise you there is a state called the 1710. Interesting thing, for example, about this state is this is one of these nonets that we've been talking about, right? That I've been introducing to you. All these beloved nonets that allow us to classify states. This is what the quark model predicts as a nonet. But there is an extra state, this one. There should be only 9, but there's a 10th one with more or less that mass. What is that gap? It must be something else. It cannot be a quark model prediction, because it's not. So this guy, the global, we'll talk about that. What happens with the states that don't have these quantum numbers that we were speaking before? what happens with this 1 minus plus hybrid thing? Well, the picture is even more complicated because if you do lattice QCD calculations, you expect 1 to exist. But then you go to the PDG, and it seems like there exists 2, and no theoretical prediction ever predicted 2. So we're seriously misunderstanding something. It's this like both hybrids. We'll talk about that. And now we won't talk about the huge plethora of possible exotics that you can look at these quantum numbers. Many of these states are not described in this table. And these are all in Charmonian. These are basically most of them Charmonian measures. So X, Y, Z. And we have a program to study them in the future here at Jefferson Lab. So, well, stay tuned tomorrow morning, Friday morning. We will talk about these exotics.
Very much, Arkaitz. So now this is followed by an informal discussion that should go until 4:15, we'd say. We can be not that strict with that. And then at 4:30 we have the social. So it's an open space for more questions or discussion,